In this video, which is our last one for chapter 12, we're going to talk about the concept of polarity that we went over way back in the first video. And instead of being based on one bond, we're going to extend it to an entire molecule. Right? So you're going to need something to write with and something to write on. Once you have those, let's go. Okay, so as we kind of talked about previously, if a bond has an uneven distribution of charge because one side has a higher electronegativity than the other, that bond is polar. The side with the higher electronegativity will be negative. The side with the lower electronegativity will be positive. That's why we call it electronegativity. We can expand this to cover the entire molecule, right? So if the entire molecule has an uneven distribution, so if one side is positive while the other side is negative, the molecule is polar. It has what we call a dipole. The easy way to determine if a molecule is polar is it has to A, have at least one polar bond, so one bond between different atoms, and B, all the domains cannot be identical. If all the domains are identical, then what's going to happen is that those dipoles in 3 dimensions will wind up canceling each other out, right? So if I have one pointing to the top, one pointing to the bottom, one pointing to the left, one pointing to the right, and they're all the same, they all cancel out. So even if every bond is polar, when you do it on a molecular scale, it is possible to cancel them out. So we want to see the domains in the center atom are different. And I'll give you 3 different examples. 2 of them are polar, 1 of them is not. And we'll kind of go through how they work. So first molecule, everybody's favorite, water. Everyone knows that water is a polar molecule, right? The reason why is because the oxygen-hydrogen bond is actually very polar, high difference in electronegativity between oxygen and hydrogen. The oxygen side of the bond is negative, the hydrogen side of the bond is positive. So what that gives us, because of the way that water is arranged, you see those 2 little lone pairs on top, it creates that bent or Mickey Mouse looking structure. So that means that the oxygen half of the molecule on top is negative, that's outlined in red. And the hydrogen half of the molecule is positive, which makes it blue. Top half red, bottom half blue. That is a distribution in charge. That is polar. Our next molecule, the same one we drew as our first Lewis structure, formaldehyde. The carbon-oxygen bond is polar. The carbon-hydrogen bond, by definition, is not polar. So what we actually have is the oxygen side is negative, the carbon side is positive, right? So again, the carbon side is blue, the oxygen side is red. That's a distribution in charge. One side's plus, the other side is minus. That makes the molecule polar. And again, notice the domains are different. So for water, we had bonding domains and lone pairs, which were different. Here, we have bond to oxygen and bonds to hydrogen. Those are different. Now, for an example of a nonpolar molecule, we're going to look at carbon dioxide. Notice, both bonds in carbon dioxide are carbon-oxygen. That makes both of those bonds polar. But because those bonds are 180 degrees away from each other and pointing in exactly opposite directions with the exact opposite strength, they cancel out. So we have negative outside, positive center. In this case, we don't have plus side and minus side. We just have the entire outer shell being negative, the entire inner shell being positive. That is nonpolar because there's no distribution in charge like that. Okay, so in this case, the 2 polar bonds canceled out because they're the exact same domain, carbon bonded to oxygen. Okay, so that's polarity. We're going to practice polarity with our modeling lab and how to work through that. So you'll actually have the model kits available to be built. Now, whenever we're working with a test or a quiz, if you need to use the model kit, feel free to grab part of one and start building the molecules so you can actually kind of see them in 3 dimensions. Because I know looking at them on flat surface really makes it hard to determine whether or not the dipoles actually cancel out. It's a lot easier to do if you're looking at it physically in front of you in full 3D.